Hi Year 11. Okay, on to the structured paper, section of the paper, sorry. Question 1 then asks you to talk about alpha, beta and gamma and decide which one has the shortest range in air, which one has a negative charge, and which one is not deflected in a magnetic field. Now most people got this right, but we were a bit confused with a couple. The shortest range in air is basically how far can it travel in air. Alpha has the shortest range because it's stopped by a few centimetres of air or a piece of paper. So this is alpha. A negative charge is going to be beta because it's an electron. And an electron has a negative charge. Which one is not deflected in a magnetic field? So deflected means change direction. The only one that will go straight through is gamma, and that's because it's massless and chargeless. Okay, part B. In a famous experiment carried out in a vacuum, a very thin sheet of gold was placed in the path of alpha particles. It was found that a large number passed through the sheet with little or no deflection from their original path, and a very small number were reflected back towards the source. And it says, explain in terms of the force acting. That bit is crucial there. Why the direction of the motion of an alpha particle changes when it comes close to the nucleus of a gold atom. So, be careful with your exam technique. If it says in terms of the force, you have to have reference to force in your answer. You need to talk about the motion, an alpha particle, and a nucleus of a gold atom. All of those things need to be referenced. So, we're going to say an alpha particle and a gold nucleus both have a positive charge. So an alpha particle coming close to the gold nucleus will be repelled. Okay, sorry about the very weird lighting here. Now, the force acting here is this repulsion, and we've explained why that repulsion occurs, because they both have positive charges and like charges repel each other. So that's part I. And then in part II, you're asked to state some conclusions about the nuclei of the atoms that were made from the experiment. So this is Rutherford's gold leaf scattering experiment with the alpha particles. We looked at that in the lesson. There are a couple of options that you could have had. So I will refer to them. You would have got, if you had said 2, you would have got the marks for 2 of them. So the first thing is for saying the nucleus is very small. Okay, now it asks you for the conclusions about the nuclei, so you really want to refer to the nucleus, but in this case, if you'd have said the atom is mostly empty space, they let you get away with that and they gave you a mark. So that's one of the things that you could have said. You could also have said the nucleus is positively charged. That was something else they discovered from the experiment. You could have said it contains protons. You could have said the nucleus is very heavy. Sorry, I can't spell today. Or you could have said has most of the mass of the atom. Now, a few people in that last bit said the nucleus has mass. That's not enough, because you need to imply that you realise that most of the mass is in the atom, or it's a very dense, very heavy thing, rather than just the fact that it has mass. So that is question 1. Okay, question 2. An atom consists of a nucleus made up of protons and neutrons surrounded by orbiting electrons. Which of these particles has a positive charge? I think nearly everyone got that right and wrote proton. Which of these two particles have almost equal mass? Now this is where we were getting a little bit more confused. So it's a proton and it's a neutron. Okay, electrons are tiny in comparison to protons and neutrons. They whiz around the outside. They're much, much smaller, so just be careful there. Also, a surprising number of people got part B wrong. So this is something that I didn't spend too much time on because I thought that chemistry would have helped us out there. Remember that whatever you learn in another subject also applies here. So here you can see silver, and its mass number is 107 and its atomic number is 47. The atomic number tells us the number of protons, so that number goes here, that's 47. And then the difference, because remember this top number is the protons plus the neutrons, so the difference between these two gives me the number of neutrons, and that's 60. So to get that I did 107 minus 47, just to be clear. Okay, let's go to the graph, and you can see that they plot the count rate against time. Now a big issue that we had with this question is people misread the time zero count rate. Okay, they said that was 300 and it's not. Okay, you should see that that is 320 at time is 0. Okay, so that was a bit of an issue. So you're asked to use the graph to find the half-life of this nucleus. Well, if at time 0 I've got 320 count rates, then if I half that number, I'm going to get 160. Okay, so what I need to look at is 160, 1, 2, 3, 4, 5, 6, and at that point I can track across, and when I do that I should reach the correct value for half-life. Now if you don't do that carefully, if you're out by even a small square up here, you're going to be out down here. And there's a very small tolerance that was allowed. So hopefully you can see on this set of axes, each two little squares, 1, 2, 3, 4, 5, is 1. Okay, so this here is 8. Lots of people rushed this and wrote 5.6. So just check your scale a bit more carefully. Okay, so I'm now just going to put 8 and check the graph. It's measured in hours. Okay, then it asks you to plot 2 more points on figure 11.1 at times greater than 10 hours. So we know that one half-life took 8 hours, so another 8 hours later will be 16 hours and then 24 hours. Okay, now at 8 I had 160. So 8 hours later that will half again. That should be a count rate of 80. And then another 8 hours later that will be at 40. So that will allow me to plot my graph. I might choose a different colour, sorry, just so it shows up a little bit better on the video. Sorry, useless here. Okay, so we're going to look over to 16 and 1, 2, 3, 4 at 24 as well. So at 16 I know that I am plotting at 80 and I know that at 24 it's at 40. So I've got 1, 2, 3, 4. Okay, so it also says, if you look a bit more clearly further down, that you need to use a dot in a circle to indicate each point. Now, I've actually not read that cleverly beforehand, but basically, if you just put a circle around your point, that would be helpful. And then you need to, in fact, no, you don't. All it says is plot 2 more points at times greater. So you don't even need to finish the line of best fit there, or the curve of best fit. That won't be necessary for the marks. Okay, question 3. Here we go. In a lab experiment, we've got an isotope. Again, we want to be using exam technique. You want to highlight key terms in the question so that you really focus in on what is being asked of you. So we've got an isotope used as a source of alpha particles, and it says, state one feature of uranium-238 nuclei that is the same for the nuclei of other uranium isotopes. Now, lots of people were telling me lots of good facts about uranium, but they just weren't to do with the nucleus, and they weren't to do with isotopes, so they weren't reading exactly what the question was asking of them. So we know that an isotope of an element is one that has the same number of protons but a different number of neutrons. So a feature that is the same for the nuclei of the isotope is the number of protons. Now, some people just wrote the word protons. That's not going to be enough to get you the mark. Okay, what about the protons? The smell of them, the colour of them? You need to be more specific, so it's the number that are there. And then obviously for something that is different in the isotope is then going to be the number of neutrons. Okay, so then we get to the 4 marker. I was genuinely really pleased with how everyone did, generally speaking, with this question. So it gave you the diagram where we've got the alpha particles hitting the thin gold foil, and we know that in most cases it will just travel straight through and reach over here. And so for the most part we'll detect lots of alpha particles here, but then less frequently some will be deflected off and we'll find them here, or we'll find them here. And then even more rarely they'll bounce back and we'll find them back in the direction that the alpha particles came from. So we've looked at that experiment, we've seen that on a few videos, we've discussed it. Now we have to work on our exam technique. So it says, to investigate the scattering of alpha particles, a detector is moved to different positions and the measurements are recorded. Describe the results from this scattering experiment and explain what they show. 4 marks. Lots of people jumped straight to the explaining and didn't mention what they actually would find happen. So that's an issue. And the other issue is on the mark scheme, there are M marks and A marks. So an M mark and an A mark is linked in GCSE Physics. If you get the M mark, you are allowed to get the A mark. If you haven't written what is required for the M mark on the mark scheme, even if you've written the A mark, you don't get any credit for it. Okay, so some of you might have written the explanation bits, but you don't get any credit for it because you didn't tell me what happened in the experiment in the first place. So we have to say most alpha particles travel straight through the gold foil undeflected. Okay, that is describing the result. The result that we found in the experiment is this: most alpha particles travel straight through. The explanation that we get from that, the atom is therefore mostly empty space. Okay, so we've got a describe to do and an explain. This bit is the describing what we saw. This bit is the explanation that we have because of that. Okay, so that's the first set, so that's worth 2 marks. And then we say a small number of alpha particles are deflected by the gold foil. Okay, therefore the mass of the atom is concentrated, so it's found in a small or very small nucleus. Okay, or you could also have said, and the nucleus is positive. Okay, so again, the description of what was found in the experiment is here. A small number are deflected by the gold foil. What we know from that is the explanation, and that's there for you. Okay, so that one there, really for a lot of you, was actually exam technique rather than not knowing it, for the reason why you may have lost those marks. But lots of you did really, really wonderful written answers there, and for 4 marks, I was really impressed, so good job. Okay, are we at our last one? No, second to last one. Sorry for a very long video here. Alright, so an underground water pipe has cracked and the water is leaking. You've got an image here. Here's the technician. He's on the top of the ground. He wants to know where the crack is, deep underground. So he adds a radioactive isotope into the water supply. Now remember, the water is travelling through this pipe. Okay, so I'm just going to add some dots to represent the water emitting radiation. And obviously the technician is trying to count that, so he's trying to see how much radiation comes through the ground to him. Okay, now what will happen is not much radiation will get through the metal pipe, but where there is a crack and there is a hole, lots more radiation will be able to seep through that mud, okay, because there's not the metal there to absorb the radiation from the water. So he's basically going around looking along the pipe, trying to find where the count rate goes up. So the question asks you to state, so say and explain why the type of radiation must be emitted by the isotope to be found, for the leak to be found. Sorry, words not coming out today. So we know, going back to the diagram, that alpha is going to be stopped by the mud for sure, even where we get to the leak. Okay, we also know that beta will be stopped by that bigger distance. Okay, think about the size of the person. That's like 2 meters, so that's probably a good 2 meters, and a lot of that will also have been absorbed by the water itself, so we won't get very much discrepancy or difference between the amount of beta that we see here and here. Okay, it'll be very similar, so that's not a good option either. So the best type is going to be gamma. Okay, and we can say it is the most penetrating, and therefore it will get to the ground, above the ground, or will go through the ground for several meters. Okay, so that mud could be really thick and it wouldn't matter. The gamma would get through it, whereas alpha and beta would not. Okay, so it would be 1 mark for the stating and it would be 1 mark for the explaining. Most of you got that, to be fair. The half-life of the isotope is 6 hours. And it's asking you to explain why that is a good choice of isotope. So, we know that we've put the isotope into the water supply. Okay, that's being used to drink, that's being used to bathe, that kind of thing. So, we can say it's a long enough half-life for the technician to find the leak. That's worth 1 mark. Okay, that's a good reason why 6 hours as a half-life is helpful in this case. He might need quite a while. We don't know how long that water pipe is. Okay, it's short enough to disappear out of the water supply quickly. Okay, so what we mean by that is it's not going to be staying in the water for ages and ages and contaminating it for people. Okay, so people could be told that they won't be able to use their water for 6 hours, but then they get it back. So obviously that's a safety issue. So that's the 2 reasons why that's good. I think we finally made it to the last question, I hope. I've been talking for 20 minutes, goodness me. Okay, so we have a radioactive material X with a half-life of 2 minutes. At the beginning of the experiment, the count rate is 800 counts per second. And then we're given, let me zoom out, sorry, the count rate readings at the start of the experiment after 1 half-life. So we can see that 800 reduces to 400 in 2 minutes. Let's zoom out a little bit more so we can get the whole graph in, hopefully. Maybe not. There we go, that'll do. Okay, so I know that I'm about to be asked to plot the rest of the graph for up to 12 minutes. So I'm going to need 4, 6, 8, 10 and 12 plotted. We know that the half-life is 2 minutes, so after 2 the next one is going to be 4, and the point 400 will have decayed by half, so it will get to 200. So at 4 I plot at 200. 200 halves to 100 another 2 minutes later. That then halves to 50 at 8 minutes. At 10 minutes that's going to halve again to 25. And then at 12 minutes that then will halve again to 12.5. So there's 10, it's about there. Okay. Now the next thing, if I just show you on the next page, sorry, is that you get 3 points or 3 marks for completing this. Draw the best curve through your points. Now, you want to be very, very careful when you're plotting that you do this smoothly. I could see a lot of sketchiness where there were multiple lines, so it looked a little bit like this. That's no good because I can't decide which bit to look at if you do that. So I need one really thin, crisp line. So I always want you to have a really sharp pencil when you do this. And then I'm just looking for a reasonable curve. So it's often easier to do it lighter on the page, so don't hold it too hard. And that also allows you to let go a little bit. If you can do it all in one go, that's absolutely fine. That's probably better and less wobbly than mine. But what you just want to be careful of is that you're getting through the points as best as possible. Quite a few of you were out a little bit, and that might be why you lost a mark. Okay, so then it asks you to find the count rate from the sample after 9 minutes. So here we go, let's look at 9, which is here. I'm going to get my ruler and track that across. Hopefully you can see that that occurs at 30. Okay, so at 9 minutes the count rate will be 30. Now if you didn't plot your curve smoothly, yours might have been out. So I was looking for a value between 30 and 35, that's what the exam board would have allowed. If you plotted yours wildly wrong, I will have read yours and given you a mark for that. Okay, it then asks you to check, let me pull this down, the time it takes for the count rate to fall from 700 to 350. So at 750, which is here, I was about there. Okay, so that's about 0.2 minutes. And then by the time it reached 350, I'll zoom out in a second so you can see this, it was about here. And I make that 2.4 minutes. Okay, so that on my graph gives me about 2.2 minutes difference between those points. The correct answer, if you'd have done the most perfect curve, would have been 2 minutes, but I would have given you that. So here, the time it takes for the count to go from 700 to 350, I'm putting 2.2 minutes. That might be different for you because your graph is slightly different, but if it was wildly out, that's a bit of a problem. In part C, it then asks what the half-life of the sample is. Now, you already gave me a value from 700 to 350, so this here is the half-life, and that's constant the whole time. So whatever value you put there needs to go down here. Okay, otherwise you're contradicting yourself. So that's also 2.2 minutes on mine, but on yours it might have been slightly different depending on your curve. Okay, last bit, we're almost there. So a river contains fine particles of mud. You have to explain why the radioactive material X is not suitable to trace the movement of dumped mud. Well, we've just said that the half-life is 2.2 minutes. People can't do their jobs in 2.2 minutes. Moving mud at sea with large ships, the time frame is not going to be that quick. So the half-life is too short. Okay, so then it asks you to list 2 properties that would make it suitable for tracking the mud. Okay, and lots of you said it needs to be highly penetrating, which is good because it needs to get through the mud. But lots of you then also said that it needs to be not very ionizing. Unfortunately, that doesn't get you a mark because it kind of means the same thing as this. And actually, it doesn't make a difference whether it's ionizing or not, how good it is at tracking the mud. Okay, so what we want to say is that it has a long half-life. Or we might want to say it's a gamma emitter. That would also get you a mark. You could also have said it has a similar particle size or density to the mud. I think it's less likely that you would come up with that in the exam though. Hopefully that's helpful for you.